Hey, beautiful people. Welcome to another morning, midday, afternoon, night of maths. This is the Free Teach channel, as you probably know when you click on it. Hopefully, anyway, it comes up. One day I'll get paid by YouTube for it. Today we're looking at combining geometric growth and decay. So you're probably partly asking yourself, if you haven't read into it, how do you combine growth and decay and come out with something that's not different from what you started with? And that is by having something, a growth or a decay factor that's different from the other. Okay, so what that means, so we're going to do this using recurrence relations to start with. So V0, we should be getting familiar with, that's our starting value. Vn plus 1 is the building, how we build our recurrence relation. R, the rate of increase or decrease, growth or decay, times Vn, whatever your value was, starting at the starting value, plus or minus D, the common difference. Okay, so if you had super, you might be paying into it, you might be getting interest. So this is an R that's over 1, and you may also be adding money to it. If it was a loan, you may owe money. This may still be over 1, but this will be a subtraction. You're trying to take money or pay off that loan. Okay, so firstly, generating a sequence by hand. So we're given an example where we've got V0 is equal to 3, Vn plus 1 equals 4 times Vn minus 1. Okay, so if we want to generate a sequence using that, the first, we know that V0 is 3, so the first number in the sequence after that is V0 plus 1, and that is equal to 4 times V0, which is 3, minus 1. So 4 times 3 is 12, minus 1 is 11. So that is equal to 11. Then, after that, we can just replace the 3 with the 11. So 4 times 11 minus 1. Okay, so all I've done, taken that, placed it there, because 3 is our Vn. So this is effectively V1 plus 1. And 4 times 11 is 44. Take 1 is 43. And we keep going. 4 times 43. So 4 4s are, well, 4 40s are 120. 4 3s are 12. So we should be looking at 4 40s are 160. And 4 3s are 170, 12. So that gives us 172 minus 1 gives me 171. And this one, I'm not going to bother working out in my head, throw out the calculator. Four times 171 is 684. Take 1 is equal to 683. So that's building our recurrence relation as we go along. Okay. Over here we have a problem regarding recurrence relations. So we're modeling a population change in this one. So to keep it nice, we've got a trout farm, fish farm. TN can be modeled using the recurrence relation, So we have 10,000 fish to start with. Okay. They breed at a rate of 1.1. Okay, so a 10% increase on the current population. Okay, so N is months. So every month we get an increase of 10%. And the fish farm takes out 3,000 fish every month. Okay, use the recurrence relation. Oops, made a boo-boo there. That should be 2 months, not 22 months. Use the recurrence relation to determine the number of trout in the pond after 2 months. So question 1. after 2 months, we'll go, so T1, so month 1, T0 plus 1 is going to be equal to 1.1 times Tn, which is 10,000, minus 3,000. Okay. And that will give us 1.1. Jump over the calculator. So our answer is 8,000 for T1. So after 2 months, T1 plus 1 is equal to 1.1 times 8,000, 0, not a 6, minus 3,000. Okay, hopefully we can see what's going to happen here. We're going to get our population dropping again. So I can just go and multiply that by 1.1 and subtract 3,000 from it. Okay, because our bid mass operations, our order of operations, the calculator will always do that in the right order. So it'll multiply by your 8,000, which was our last answer, and then take the 3,000. And after 2 months, oops, switch screens too quick. After 2 months, our trout farm population is down to 5,800 fish. Okay, so 5,800. After how many months will there be no trout left in the pond? Okay. So we want to keep going with this to the point that we cross the zeros into the negatives or hit zero exactly. Okay. Now, for some tasks, this could take quite a while. So what we want, especially with a recurrence relation, so what we want to be able to do is perform it on the calculator. Any calculator basically does it the same way. We will put in our V0 or our T0 value. So we'll put in 10,000, and depending on what sort of, it's common to have an execute button, we'll hit execute. Then after that, we will punch in multiplied by R, which is 1.1, subtract 3,000, and hit execute again. And again and again and again until we get to the 0 point. You just have to make sure that you keep track of how many times you hit this execute button. Okay, not this one here. So what number of times do we hit execute there? Okay, so we'll punch that into either CAS, scientific calculator, they're all going to work the same. So we've got, just clear that. I know that we've done this once already, so I'll just demonstrate it for good housekeeping. 10,000 equals. Then we're going to multiply that by 1.1 and subtract 3,000 off it every time. And hit equals. Okay, so that's 1, 2, 3, 4, 5. Okay, so we get 5 times before it goes under. Okay. So to give our, even though it's gone well under, the term before that was above 0. Okay, so that after 4 iterations of the recurrence relation, we still had 718 fish left. So it's after the 5th one. All right, so we say that after five months, there'll be no fish left. Okay, hopefully that's fairly straightforward. The process is pretty simple, and we will see you next time on Free Teach. Give it a thumbs up and subscribe and comment if you'd like to see something else. Cheers, gang. Bye.